All right. What you all really want to know about. Let's see. Yeah, this is the page I want. Overall, I was pleased with the exam. I hope you will be too, but there's always some people that aren't, obviously, because that's, no matter what exam I give, there's always a distribution. And, yes, some people flunked and some people aced it. So I do have the results back, and I will have I've created the solutions. So the thing you saw with the right answer and my explanation will be on WebAssign in the resources, there with the syllabus and the superhero paper, before I leave in a few hours. So you can go read see what was right, you can tell what you missed, and why it's right. Boy, that was smooth. Okay. Unless you're just dying at this very second to know something and can't wait a few hours, I would like to let you see them all, and you can look them over. And that way Monday, if you got questions or think, that's just absurd, you can let me know. Does that seem groovy with you folks? All right. The average was, I was sure average, that's a vague term, depends on which way you figure it out. The arithmetic mean was 75, which I guess is technically average. The median, though, where half of you were on one side and half on the other, was 77. So just under a B was where the middle was. The more I think about it, that's a pretty good distribution. Somebody aced it. There were, see how many people took it. I don't know. I didn't figure out the percentage, but there were 11 or so A's, so it wasn't that bad. There were 6 F's. I always wonder what that means. Didn't try, didn't study, weren't in class. I don't know. I'm looking over the questions. I have a percentage of who missed what with each question. So after you guys have looked it over, we can go through that. I'm big. This is your wink wink. That common ones that were missed on the exams, I like to revisit. I always consider them for the final. Hence, make sure you know this stuff, because I will test you on it again. They'll just, in less detail, because we have to cover everything at the end. So I hope you get that sheet. Questions or concerns right now? Yeah. Oh, the quickest way is I'm posting the solutions and before I go home, and you can look and see and figure it out yourself. Your actual grades aren't in WebAssign, because it wasn't one of the assignments you went, so it doesn't have it there automatically. No, I haven't entered. I'm keeping an Excel sheet to tell you the truth, because we have the participation points, which since the bookstore works it out that the clickers are registered through WebCT. That's how I have to export them to there to get all your grades. And WebAssign is how we're doing homework. And exams I'm doing independently, so I'm just combining all in Excel. I can tell anybody what they got if you email me, right, if you can't wait that long. But yeah, I'm going to get them in there so you can see them, of course. But that won't be this afternoon. Also, then I put an announcement on WebAssign, lest you forget what I'm about ready to say or aren't here to listen to me. I put when exam 2 is going to be, and kind of a rough schedule of my pace till then. What chapters we're covering, 6 and 7, part of 10, projectile motion only, and then 13 and 14, fluids. So you can, it's there on the announcement in case you want to get ahead. And the next homework is now available for you, which will be due, I think I made it the 13th, so you have over a week to do it. It'll be on chapters 6 and 7. We're going to start momentum and energy today. Excuse me. And that's what the first homework's over. 6 and 7, momentum and energy, in my mind seem more heavy, intense, more there, substance. So we'll spend slightly longer on those two than 13 and 14, if you want to just know going in. Who's read chapter 6 already? Hey, good for you. This lecture will make a lot more sense to you. Okay. Momentum. In my mind, momentum is, okay, I'm sure. Who in here has never heard of the word momentum? That's what I thought. Let me just turn it back on you. If you had to explain to your mother right now what momentum was and you hadn't read chapter 6, what do you tell her? Hey, Johnny, what's momentum? You're in a physics class. I don't know yet. We haven't gotten there. Well, what do you think it is? And you say? All right, yeah, it's something in motion. Yeah, something's going forward and it's kind of hard to stop. But it can switch, and it's related to energy. This is good. Anybody want to add to that? That's okay. In my mind, it's somewhere in between inertia. I'll build on that then. We have this inertia that we learned about. Things that are at rest want to stay at rest. Things in motion want to stay in motion. But we use energy more often than momentum, I think. It's kind of the thing in the middle. I like to sum it up, as does the author. That's why I like this book. Momentum is like inertia in motion. Inertia in motion. Inertia is kind of vague for a lot of people. Hopefully not as much to you now. And you can't really say, that has this much inertia, and give it a quantity. Momentum and energy, it allows us to be a little more quantitative, which some of you might not like, but some of you will, than qualitative. Well, how much inertia does it have? Well, it's more than this. Well, how do you know? And we related to mass. Mass helped us get a gauge of the inertia. It didn't tell us what its inertia was, but we knew inertia was related to mass. The more massive something is, the more inertia it has, and the more it wants to resist motion or change in motion. So momentum is better. We can kind of qualify it. And it makes sense to what's hopefully already in your heads. Would you rather catch this when I throw it at you or catch this? The little one. And that has to do with momentum. Before you looked at it as inertia. But now they have inertia in motion. And this one is going to have more momentum than this one if I throw them at the same speed. And so not only do we look at mass for momentum, we look at its velocity. In physics, and the book barely mentions it, they use a lowercase p to represent momentum. And it is mass times velocity. So we consider its inertia and how hard it's going to be to resist a change in motion, but also how fast it's going matters for momentum. And that's why, let's see, on the test we did a Mack truck, a big diesel truck, and let's put little Timmy on a tricycle. Would you rather get plowed over by a Mack truck going 5 miles an hour or little Timmy going the speed of light on his tricycle? Did I ask this in this class already? That's my favorite example. Yeah, the tricycle. And you know this innately because not only does he have less mass, so he has less inertia, but he's going a lot faster. And you have to take that into consideration. That's why I hope a lot of you are leaning towards, if that's my choices, I'd rather get hit by the big diesel truck. You can have a really big mass, but if it's barely moving, the momentum might not be as large as if you have a small mass, little Timmy on the tricycle, but going really, really fast. It's the product now. You have to consider inertia in motion. Does that make sense? So yes, a bullet can have a lot of momentum. That's why it can go right through things. Little mass, not much inertia, but boy, it's going fast. So we before looked at the forces needed to stop something based on its mass. But we're going to start looking now at collisions at the end of this chapter when things run into it or you're trying to stop it or move it. And that is a big factor now. Because we'd say that momentum has a lot of that bullet has a lot of momentum. So does this though. If I just, it still had a lot of momentum even though it wasn't going that fast because the mass is big. So just don't forget the two. That's the connection. Let's see. Give you some points. And I'll do more than one, so it's worth getting it out. So let's see what you think. It's open. You can start pulling. A moving object has what? Momentum, energy, speed, or all of them? Channel 44 is correct. And I have 40-some responses, so we're getting there. Nobody's digging anymore. Most of you are in. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. Yeah, you just got it in. Look at that. Probably only one person thought it was A. Everybody else thought it was D. So A is correct. Good job. But I hope you at least thought it was C, because that was everything up till now. A moving object has speed. I hope that's a duh. I don't expect you to know energy yet, because that's next chapter, but most of you are familiar with energy, and if it's A and C, it must be D. Anyway, it does have energy as well. Something that's moving. Again, you know you don't want to get hit by that bullet. It has inertia, it has momentum, it has energy. So it's all of them. Whoop. All right. Try this one. When the speed of an object's doubled, what happens to its momentum? If you double its speed, how does that affect the momentum? Ten, 9, 8, 7, 6. We got as many as last time. Almost. So one. Now we do. Going once, going twice. Sold. Most of you thought B. You're correct. Whoop. It does double. And that's back to this. It's a direct relationship. This is a guide to thinking. If you increase the speed, momentum will increase, and directly proportional. So if you quadruple the speed, you'll quadruple the momentum. It's just there's two ways to change your momentum now. You can change the mass or the speed. So what if you double the speed, but cut the mass in half? What happens? It's the same, because one went up, one. Very good. You guys are getting it. So another term in this chapter is impulse. And that one makes more sense. And your book tells you that it is a product of a force extended over a certain period of time. And I want to impress that this really shouldn't be like a new equation. It's just a new term. Inertia in motion, we're going to call momentum now. And a force that you guys should know, in order to change something's motion, to get it moving or to stop it moving or to redirect it, you have to apply a force to accelerate it. Acceleration is a change in velocity. Well, you can't apply a force for no time. Okay, you can, but then you're not applying it. So in order to, in real life, apply a force, it's going to take a certain amount of time. So to catch this when I throw it at you and stop it, change its momentum from a lot to nothing, because once you stop it, it has no momentum. It has inertia, but it has no momentum. That will require a force, and you'll have to apply that over a certain amount of time. So we call that impulse. Apply a force for a certain amount of time. That's all there is to that one. Go. When the force that produces an impulse acts for twice as much time, what happens to the impulse? This is why I like equations. If you're not getting it, well, most of you are, it looks like. If you can't remember the concept, sometimes you can just go back to the shorthand and realize, oh, that helps me remember the relationship, and it seems clearer to me sometimes. Oh, a couple of you aren't voting yet this time. 5, 4, 3, 2, 1. Overwhelmingly, 90% B. You're right. Good for you. Same game. We play that balance act. You increase this, that goes up. So you can catch this different ways, can't you? Most of you, when you catch it, probably just like, and I'm not exaggerating, as opposed to, if I try to do that with this, what do I physically have to do? This, oh, that hurts. Sorry about that. Still work? Sorry. As opposed to this. Anyway, in terms of force, that's what I'm getting at. Which one do you think I have to exert more force on? I'm exerting a force on the medicine ball. Which one how do you think the forces compare between this and this? The first one's higher?
Well, the amount of force you apply over the amount of time is higher.
The amount of force, so, okay, what you're saying I go with, just be more definitive. I want the force. A, that force, or B, that force. That's true, but you haven't told me which force is bigger yet. We got an equal vote. Who wants to agree with equal? It doesn't matter, they're the same. Few of you. Who thinks A, catching it like this, is more? Less? You guys aren't voting. Do I have to make it a clicker question? Everything a clicker question? Not sure. Well, that's good. That's why we're having this class. Okay, just look at my face, and I won't exaggerate, and what do you think? Versus that one requires more force. And the reason is impulse is a change in momentum. And I'll continue this in a moment. Yes?
Since impulse is force times time, the more time that you're in contact applying force on the medicine ball, the lower the impulse is going to be. The higher it's going to be. So you're acting more on the momentum of the medicine ball.
Mostly. So let me specify. This force is applied for a certain amount of time. And I'm glad you guys realize it, that I'm applying a force for more time here as opposed to here. There's less time. What I didn't expect you to know yet is this is changing its momentum. I'm applying a force for a given amount of time. And what that does, the next section in the chapter, is an impulse, that force over time, causes a change in momentum. This ball has mass and it's going yay fast right before I catch it. So if I try to throw it the same height so that it's fallen the same distance, right now versus right now. If it falls the same distance, it's going the same speed right when I start to catch it. And so it has the same amount of momentum right before. Do you see that? It's the same mass going the same speed right before I catch it, either case. Do you see that? Somebody nod or something. No, okay. Do you believe, let's do it with this one. I'm getting tired. If I drop it from the same height, right when before it hits the table, how does its speed change from this to this to this? How's the force right before it hits the table? Did I just say force? Let me rephrase so there's not confusion. I meant velocity. It's speed right before it hits the table. I'm being confusing, obviously. If I drop it from this height, it's going yay fast right before it hits the table. How does that speed compare to that case versus that case? It's the same. What I'm trying to emphasize is that they're going the same speed right before it hits the table. So is this. When I toss it up, right before I catch it, it's going the same speed. And so it has this, I'm not changing its mass, and it starts out at the same speed. So it comes in right before I catch it, it has the same momentum. That's what I'm trying to get at. Is that clear? Right before I catch it, it has the same momentum in either case. What I'm going to do now is apply a force for a certain amount of time to change that momentum. I'm going to make this guy stop. I catch it. I just do that two different ways. This way or all at once. So the change in momentum is going to compare how? The change in momentum. Right before I catch it, they have the same momentum. And I'm going to stop the ball in both cases. There is a difference in the amount of time. I want to know the change in momentum. It's going to start out, let's say, mv. It's going mv in both cases. What's it going to end up as after I catch it? We got a negative and we got a 0. Somebody break the tie. We got another, the velocity is 0. So the momentum will be 0. So they both start out as mv in both cases. They both end up as 0. Can you see now that the change in momentum will be the same in both cases? The change in momentum. The change in momentum. It sounds like I'm being redundant, but somebody will get confused again. The change is the same. Now the way I did that was differently. I exerted a force to make that change. And that's the point of this equation. Impulse causes changes in momentum because that's you're applying the force. So if the change, this side of the equation, is the same, and you guys correctly observed that in one case the time was longer than the other, can you tell me now which one had a greater force? Yeah. See, and you've learned the hardest thing in this chapter. That's right. So basically, we're playing. The change in momentum was the same in both cases, because it went from a certain speed to 0, both of them. But one took a lot of force quickly, and another one needed force longer amount of time. And so something can have so much momentum, and when you try to change that momentum by putting an impulse on it, a force over time, you have a little play there. Do it all at once. Sure, you'll stop it. It'll have the same effect, but it'll require more force. If you want to not hurt as much, like in this case, yeah, make it take a little longer. Then I don't have to apply as much force on the ball for the same effect. We'll revisit this, other examples. Do you have something, Kate? I'm glad you asked. Acceleration, we learned, in order to have a change in velocity, a change in motion, you had to apply a force. But it depended on how much inertia the thing had. We used mass. So there's Newton's second law. That's how we produce a change. That's why we have to apply a force to cause a change. We also learned that acceleration is a change in velocity. So I'm just going to put these two together. Some of you will like this, some of you won't. Because, you know, it looks like math. If these are the same thing, then they're equal. Do you at least see that? Don't want to lose anybody here. Well, if I remove the A, those are equal. And for those of you that are familiar with cross multiplying, that's what I'm going to do. If you're not, multiply both sides by t. And the t will go cancel over here, and you'll have a t on this side. Then multiply both sides by m. The m's will cancel on this side and end up over there. You get, that equation. So that's how acceleration comes into it. This force causes a mass to accelerate for a certain amount of time. But basically, we're just putting the time over here now. Remember, a change in velocity over time is an acceleration? Just move the t over here. If you apply a force for a given amount of time, we're now going to cause this mass to change its speed. We call this momentum now. Inertia in motion. So the end of this chapter gets into collisions, and I intend to do lots of examples. Let's see, get some today. Let's do another one right now. Who fancies themselves as a pitcher? You think you can aim at least somewhat good? None of you? All right, sold. And then I need 2 more volunteers. Please. We're going to have her throw an egg into this sheet. I need 2 people to hold this sheet. We'll have you over here. And I just need 2 people to hold this up. Great. 1. And how about you right here and you right here? And, yeah, with the hand you just grabbed, your left, your right. Hold that up high. And then with your other hand, grab the other corner. Right, now, just like that. Hold that up as high as you can reach and leave this sagged a little. And you, wherever you feel comfortable, it's more important you don't miss for their sake than anything else. But we want to see if you can break this egg. I'm prepared to watch the sheet. I want you to throw it as hard as you feel comfortable with accuracy into that sheet, but your intent is to break the egg. You can even get closer if you think it'll help. Try again. That was pretty good though. Here, just use this one. That way they don't hit each other. That was a good throw though. Come on, break it. You want another shot?
No, it's not going to break.
Yeah, you're right. Thanks, guys. Do you know why?
Yep.
What? Here, help me be teacher.
The sheet is
Oh, you know what?
the sheet's taking some of the force from it, so extending the amount of time. So if I were to throw an egg at the brick wall, it would completely stop the egg in a less amount of time.
Very good. Very good. Thank you. Thanks for helping and being brave sheet holders too. If she, I liked your example, threw it against the brick wall, we just moved the sheet, how would the change in momentum compare to the two cases? It's the same. The change in momentum, it's the same egg, same mass, and if she throws it consistently, same speed going in, right? So it comes in with the same momentum, and the sheet and the wall are both going to stop it. So its final momentum will be 0. So it's going to have the same change in momentum, taking the same moving egg and trying to stop it. Do you see that they're the same now? You sure? So the change in momentum is the same, so it's the same game. We can stop the egg quickly, which will require more force, brick wall. Or we can apply less force, but we'll need to do it for more time. We extended the time of the collision, and so the egg exerts less force on the sheet. And Newton's third law says the sheet exerts that same little force back on the egg. The egg feels that littler force. The egg here exerts a force on the wall, and the wall exerts it back, but that force is bigger, wall, than on the sheet and back on the egg. Yeah, when you'd rather land on a pillow than the ground. And this is exactly why. A pillow or a pad or an airbag or a helmet extend the time of collision. You're going yay fast, and you're going to end up stopping. So you have a change in momentum. Do you want to do that quickly? Ouch! Or take more time, and you can still have the same effect, but you don't need as much force to do it. You just have to do it for longer.
So how's the change in momentum equal if they're taking different times to get to 0?
That's the beauty of momentum. Time isn't in this one. We took it out. In Newton's second law, if we wrote it, why do I always do that? If we wrote it as F equals ma, and a is a change in velocity over time, if time's involved, that's a force. We're looking at the force. But if you move this over here to this side of the equation, you can rewrite it, and now impulse is a change in momentum. Time doesn't matter. It's just mass and speed, velocity. So, just repeating, time doesn't matter for momentum. And impulse is this. That's a good question. I'm going to ask the class. Okay, I told you that the change in momentum of the egg, hitting the brick or hitting the sheet, was the... How do the impulses compare? Good, I'm glad I asked. See, you're not alone. The change in momentum is the same, correct? You agree with that? Impulse. What is impulse? There's two ways to think of impulse. One, it's a force over times a time. The second way is a change in momentum. An impulse provides a change in momentum. Do you see that they're equal? So if the change in momentum is the same, so is the impulse. Impulse is change in momentum. That's what the equation in the box tells us, or sums up. To provide a change in momentum, you must apply an impulse, which is a force over time. Force through a time, I should say, so you don't get confused.
We didn't have that sheet really tight on both ends, would it, the egg broke?
If you had held the sheet more rigid, what would that have done to the time of impact? Would have made it shorter. The egg would have felt more force. Would it have changed the impulse? No. Would it have changed the change in momentum? No. Same thing. But yeah, you make it stiffer, less time of impact, there would be more force, and it'd be more likely to break.
So impulse is sort of like acceleration or deceleration, or not?
I can agree with sort of, but it's not the same thing as acceleration. Impulse is not acceleration. Acceleration is a change in velocity.
It is slowing down.
Yes, that force applied. If you apply a force, we learned this F, this F, this F, they're all force. If you apply a force, then a change in velocity is occurring. Something is accelerating or decelerating. Yes. So it's changing its motion. And this force, we're going to see a change in motion. The thing's going to either speed up or slow down. And so that's why we get a change in that case, a velocity is normally what we see, because usually we don't deal with things where the mass changes, but that can happen. A rocket losing its fuel, as it gets less and less massive, it's changing its momentum. But normally we see it in a change in velocity. Yeah, force, there is an acceleration. Everything we learn still holds true. That's how we get to this point.
If they were to time the sheet, would that change the force on it?
Yes.
And then that would change the
Yeah, if we made the sheet stiffer, that's in effectly making the time of collision not quite so long, a little smaller, and so this would have to be a little bigger to produce the same impulse, because this is impulse. The product's staying the same because we've discussed that it's causing the same change in momentum, and change in momentum is impulse. So yeah, you got more concepts to think about: force, momentum, impulse, acceleration. And I'm trying to make it clear how you can at least see the difference between them.
You usually only use the term impulse when you're talking about collisions. Is that really another?
Yeah, in my mind, yes. Yeah, impulse usually comes in when I'm talking about a collision.
So you don't generally acceleration, you're looking at something moving over time.
Yeah, and in all honesty too, in my career as a physicist, I really only go to impulse when I want to know about the force. In my mind, I generally think of everything as a change in momentum. You know, it's one less thing to deal with, and momentum seems to make more sense to me than impulse. They're the same thing. I always know in the back of my head. Oh, okay, a force was applied. This thing slowed down, it sped up, so its momentum changed. I know if it takes a force to do that, but I'm looking at the change in momentum. If I need to know that force, or I'm given the force, then I can remember that change in momentum is this. And these examples I'm giving you are where you have to apply it, or they don't make sense. The egg doesn't break because of this relationship. Your airbag, you don't die because the airbag slows down the collision. And I want to reemphasize again, in a car crash, you're going 75 miles an hour and you hit a brick wall. You can either smack into the dashboard or in an airbag. how do the impulses compare? They're the same. How do the change in momentums compare? Good. How do the forces compare between the two scenarios? Yeah, the dashboard, there'll be more force between you and the dashboard than between you and the airbag. And that's because the time of collision varies. Just to be technically correct, if impulse and momentum stay the same, it's impulse and change in momentum. Don't forget that word. It's key. The momentum can change, can be something, but the change in momentum might not be. We'll get to that with systems and collisions. If the change in momentum and the impulse are the same, remember there's two ways you can arrive at that change. And you can either do it this way or this way. Maybe it's let's do it. 100 newtons for 5 seconds. The impulse is 500 newton seconds. Over here, if it's 5 newtons, to have the same change, it will take how long? If it's going to be equal, this product and this product have to be equal, how long will that force have to be applied to have the same change in momentum? 100 seconds. So yes, you can have the same impulse and the same change in momentum, but it depends on how you made that change happen. Quickly or slowly? Let's do this one. Might not get to the air track. I'll bring it out next time. Yeah. See if you're getting this. Or add a little more to it. These are two of my favorite spheres. One bounces. I like to call him the happy ball. And this one, sad ball. Same mass. If I drop them from the same height, they hit with, how do their speeds compare? Yeah, right before they hit, the speeds are the same. So they have the same momentum going in. Well, what I can do is, let's take the sad ball. And let's set this up so that if I roll it down, it does not knock that block over. It has momentum, right? As it picks up and as it goes faster and faster, its momentum increases more and more. So when it hits the block, it's trying to transfer its momentum to the block, which has mass and is not moving. It currently has no momentum. It's a collision. It imparts a force for a certain amount of time. That is not enough force to knock it over. Happy ball. What do you think will happen? Nothing? Same. It'll bounce off, or the block will just go flying. Right, it's the same mass. It's going to be going the same speed before it hits. It'll have the same momentum. The block's trying to stop it and change its momentum to zero. Does this change anybody's answer? Knocks it over. So clearly, I hope, there's more force between the happy ball and the block than the sad ball and the block, because it was enough to knock it over. You can see that. And we can justify this. And there's two things going on. One, I hope you know, the happy ball had more force, so how do you think the time of that collision compared to the sad ball? Yeah, it was less time. We can't really tell, but I'm confident if we could measure it, it would be a little less time. And then we can add one more thing. Velocity is a vector. so is momentum. And you can change somebody's momentum by changing its direction. So things that bounce have a greater change in momentum than things that don't. This goes from, let's say right before it hits, its momentum is mv. 1 unit, mv. And it goes to what? 0. So its change in momentum is mv minus 0. You know, it started with this much before it hits, and after it hits, it's 0. So the change in momentum is mv. 1 mv unit. The happy ball, whee, it comes in at what momentum? So that was sad, happy. It comes in at mv. What's it end up as? Yeah, and you don't know exactly, but approximately. Is it 0? No. It's mv the other direction, right? It comes in at mv and it bounces, stores some energy, and then comes back and it rebounds back up with that energy. Almost all of it. We'll learn about energy next section. Chapter. So if it's coming in with mv and it comes out with mv, but in opposite directions, we can just say minus. If this one was plus, then the next one has to be minus, right? It's got, if we're saying coming in is positive, then the going back out is negative. Do you remember subtracting a negative is like adding? And the change is, so ideally, the happy ball has twice the change in momentum. Do you see this? Oh, good. Good enough. If it has twice the change in momentum, then it has twice the impulse. And even if these things were in contact with the wood for the same amount of time, which one should feel more force? This feels a force for a certain amount of time. If this took the same amount of time, then it's got to feel twice the force because there's twice the impulse, twice the change in momentum. So it's like 2F. And in reality, it does take a little less time, but the main reason it knocks the block over is because it bounces. Things that bounce change direction and have a greater change in momentum. So, does that make sense? Life lesson then. This ball is really the sad ball. This ball is really the happy ball. Why? Think about it. You get knocked out of the 10-story building again. You fall, you accelerate, you pick up your speed, maybe you hit terminal velocity, whatever. When you hit the ground, do you want to bounce? Or go splat? Do you know why now? Things that go splat, whoop, they look the same. They come in, this ball is trying to go from MV to 0. Great. If you bounce, you're going from MV one direction to MV the other way. It's twice the change. Think about it. It takes a certain amount of force for a certain amount of time to stop this guy. Well, it takes the same force to stop this guy, but even more force to turn around and shoot him back up. And so the force between the sad ball, and the bouncy ball on the table, it's twice the force, Newton's third law, as opposed to half the force. So if you fall out of the building, go limp so that you are less likely to bounce. People that are drunk and drive, we all hate them. Okay, we dislike them and we feel sorry for them. But quite often they don't get as injured. Why? They're all relaxed. They're limp. And so if they get in a car accident, they kind of go splat more than bouncing off the windshield because they're all tense. Things that bounce have a greater change in momentum and require more force to make that change. There we go. Unless there's any last minute questions. Tablecloth trick, yeah? A karate chop, yes. I did, yeah, it was the rod with a piece of paper. And when we did a karate chop, it allowed us to do it more quickly. So you can think of the paper coming out away from the rod as a collision in reverse. Yeah, I used more force so that it would happen more quickly. That's a little different, but sure. You're making connections. That's good.